our discussion on the DRAM layout, and this is where we store architecture. And for the mainstream technology today, we use a stack capacitor and with this open bitline architecture. So we have this 6F square, the layout. And this is just one example. Later we will see some real examples from different companies. But the key feature of this layout, if you look at here, one of the key features is that the transistor is not, let's say, the channel direction is not perpendicular to the gate direction. So we have this angle here. So this is a twisted transistor. So the reason we have this twisted transistor is that we have to, let's say, make a space for the capacitor. Here, this circle is the capacitor. So because the capacitor is standing up, right? That means at this circle area, you cannot have wordline or bitline passing through. So you have to make that capacitor standing up without conflict with wordline or bitline. So that's why we have this here. You look at here. So then, for example, this transistor drain and source. Then let's say if the drain side is the capacitor, then you need to make this space open for the capacitor to standing up, and in this case, standing out of the plane. And then the wordline and then the bitline. So the bitline will have a bitline contact to the other terminal of the transistor. For example, in this case, source. So you have this contact here, bitline contact. So if you look at the layout here, it's like 2F for the BL and 3F for the WL, and in total you have 6F squared. So of course here I have to say that for the DRAM layout, because we care about the density, so all the design rules are special design rules for the DRAM layout. If you look at here, there's no even spacing between the, let's say, the contact to the wordline. Of course, the little bit is spacer there, but in the design rule here, we can ignore that. So this is because this is very customized and special design to push for the density, and this is only manufactured by the DRAM foundry, not DRAM foundry, DRAM vendors. So this is the 6F square layout. Any questions? And then let's look at some of the examples from different vendors. So for an example, Samsung, here we have this STC stacked capacitor 6F square layout. And this layout, in this case, the wordline is this orange one, and it's vertical. But as I said, so normally we draw word lines like rows and bit lines as columns. But here it's just rotated, but it's the same thing. So here, let's say the bit line is this yellow line, and the active area means the area for the transistor, source, channel, and drain. And then the circle again is the cell capacitor, and then bitline contact is this dot. So if you want to find the transistor direction here, is following this active area region. So we have this as one transistor, and then you know here this one because overlap with the bitline. So this must be the bitline contact here. And then the other side, this one does not connect to any wordline or bitline. That means that's a capacitor standing up. So you have this capacitor here. And then this is the area for one cell. So in this case, you can see that here the bitline pitch is 3F, wordline pitch is 2F. Why is that? So let's say from this wordline to wordline, here is 2F. And bitline to bitline, is 3F. So this may be different from this design. Let's say this one is, let me see. So this is the same, okay. So but the way we draw this just rotate by 90 degrees. So this one, the BL 3F pitch, WL 2F pitch. And this is one cell. And of course you can have other cells, another transistor here, and then you can have another cell there. This is another cell, so you have this. But equivalently, each cell occupies 3F by 2F, 6F squared. Some of the cells may share some contacts. And here are some images of the fabricated chip, like under the microscope. And this is the top view. And here is the side view to show the stack capacitor standing up. So this is Samsung, and then this is another design by this is about 10 years ago. This company called Humonda, but this company bankrupt after the 2008, the the crisis. So this memory company actually was spun off from I think Infineon before, and this used to be the second largest DRAM vendor in the 2005 or 2006 at that time. So this is another design. So you look at this design. So the difference here is the BF, let's say the bit line becomes 2F, and the word line becomes 3F. So this is just switched. So the Samsung design is bit line 3F and the word line 2F. And so the layout is a little bit different. So here again the color is the same definition as before. So but here the let's say bit line is the yellow one, and then you have the word line here. So this is the active area. So that means the transistor source drain direction. And again, this is the contact to the bit line, and this is the cell capacitor. So you have this 3F by 2F. This is one, and this is another one. So this is a different design, but very similar. So the key difference is just the BL and the WL pitch, just switched. And then for micron, so the design is a little bit different. So in this case, still 6F squared, and BL is 2F, WL is 3F. But here the active transistor, the active area has different orientation. So, for example, this is one active transistor, and here is another active transistor. So they have different orientation. Previously, here you look at here, all of them have the same orientation, the channel direction. But this one, you have this kind of twisted angle. So the advantage of this design is all the active regions can be continuous, because you can dope this region and like this. This active region can be continuous. But if you look at previous designs, then you should have isolation in between. So this is those transistors are kind of separated. So this one is kind of continuous, but the disadvantage is that the bit line becomes, not straight. So bit line not straight. Of course, for lithography, it's easier to pattern straight lines than this kind of lines with those kind of curvatures. But this one's active region is continuous, so it's easier to dope the active region, and because it's a line. And previously, the active regions are isolated regions, so you have to probably use double patterning to do two lithography there. So there are pros and cons.
The cell node contact is connected to plate or ground? The cell node.
The cell contact.
Yes.
So this one, because the cell is standing out of the plane, right? So the bottom of that cell capacitor is connecting to the drain or source or drain of that transistor, and the top is connecting outside to the plate.
So this contact goes to the plate.
Yeah. If you look at in and out, then the outside, yes, connect to the plate. So this is the layout from different companies, and still this is 10 years ago the public information that those companies published in the conferences. Today they don't disclose the detailed designs, so we don't know. But probably similar like this. Okay, so then next we are going to discuss the scaling challenges of the DRAM technology. And we are going to have two subtopics because DRAM is 1T, 1C. So we will talk about the C first, the cell capacitor, the challenges to scale the cell capacitor, and then the T, access transistor. So the DRAM scaling challenges, there are many challenges here. For example, the cell capacitor, how do you make the cell capacitor? I mean, from manufacturing point of view, because it's a very tall capacitor. And then second, the sense margin. This is what you have learned. The delta V, you have to maintain some delta V for reliable sensing. Otherwise, you may get too much error when you read out the cell. So you need to maintain some delta V. And then retention time. DRAM, you need to maintain retention time at least larger than 64 milliseconds for most of the cells. Otherwise, your error rate is too high. Then some prosthetics. So all of them will have the challenges in scaling. And let's look at the sense margin first. And we have this equation before. You have learned this before. So this is the sense margin, delta V, and then here we consider the leakage. So this is the leakage current multiplied by the refresh cycle time. Then you get the charge leaked during the refresh interval. So then, if you want to maintain the large sense margin, of course, then you want larger CS, smaller CB. And then you want to minimize the cell current. And then the process variation induced offset should be as small as possible, but very hard to control the process. So those will affect the delta V. And then the sensing speed is mostly determined by the transistor's on current for this access transistor. And then of course the prosthetics like the Wordline, Wordline resistances. So those are the parameters that will impact those metrics like the sense margin and the speed. So let's talk about the capacitor first, because we need the CS, right? We want CS to be large. And how to make CS large? We need to look at how to make this transistor. So this capacitor. So the capacitor, is basically a two-terminal structure. You have two electrodes and separated by some insulator. So the electrode can be, let's say, doped silicon, because like N+ doping to your source and drain. It's kind of contact, kind of electrode. You can have this so-called SIS structure. S is doped silicon. And you have insulator in between, for example, silicon dioxide. So this is the initial version of the capacitor. So the electrodes are the doped silicon, and the insulator is silicon dioxide. And then later industry switched to different kinds of capacitors, because ideally you want metal to be the electrode due to higher conductivity than the silicon, doped silicon. And also here for the insulator, so let's say you can change one electrode to be the metal, so it will become MIS structure. And then if you change two electrodes to be metal, so it becomes MIM structure. And this I, from the silicon dioxide, you prefer to use those materials here because of higher K value. Those are the high K material. This is because if you look at the equation for the capacitance, you know this equation very well. So it's just capacitance equals to epsilon, which is the dielectric constant, or sometimes we call it K value, times area, and divided by the thickness of the insulator. So we want large CS, so we want higher K value. So in those materials, like tungsten oxide, aluminum oxide, hafnium oxide, higher K value than silicon dioxide. So the cell capacitance typical value here, CS value, like 25 femto is the typical value for maybe, let's say, 40-50 nanometer technology nodes. And we will say that this value doesn't scale too much over the generations because you want to maintain the CS. This is the typical value. And here are some images for those capacitors, like the MIS or MIM structure. And so here this is like a two electrodes, and then this lighter color is the insulator, aluminum oxide in this case. So this is the all side view of those capacitor, stacked capacitor. So the challenge here is that we want to maintain the CS. The reason is that the CB does not scale with the scaling. The reason is that for example, if you maintain the array size or the bank size, then the number of cells per bit line makes them constant over DRAM generations. For example, you have 512 cells along the bit line. And then if you want to keep that value, or sometimes even you want to have larger value, for example, 1024 cells along the bit line. So the shorter bit line does, when you scale the technology load, of course the bit line will become shorter, but shorter bit line does not mean the CB doesn't mean CB will decrease. Why is that? Shorter bit line does not equal to smaller CB. Why is that? Any idea? Because the capacitance, is not only the bit NAND. Of course, shorter bit LAN at the same technology node means smaller capacitance. But if you are scaling the technology nodes, that means all the dimensions are shrinking. Then bit LAN to bit LAN, for example. The distance also shrink. So you are shrinking this dimension, you are shrinking this dimension. So the bit LAN capacitance does not change over generations. So if bit LAN capacitance does not change, that means your CS should not change, because you want to maintain this ratio for the delta V. So that means you have to keep CS over scaling. And here are some practical values. It says that the CS value changed from like 40 femto to 25 femto from 1980s to early 2010s. Over like 30 years, it only changed from 40 to 25. This is unlike our Moore's law, or in this business everything scales exponentially, right? This one only changed a little bit. This is because the CB does not change too much. And then CS, you have to maintain the CS. So do you see any challenges in maintaining the CS? Any idea? With the scaling? With the scaling, CB doesn't change, but CS naturally will scale, will become smaller. Why is that? If you do nothing, okay, then the CS will become smaller. Why is that? Any idea? So what determines the CS?
You're changing only the area of the capacitor, you're not changing the thickness of the dielectric?
Mm-hmm. So, again, C equals to epsilon A divided by thickness. Okay. If we do nothing, by scaling means what? So do nothing, that means epsilon doesn't change. Okay. So if you look at this, so let's say a DRAM capacitor is always like this kind of cylinder, right? So this kind of shape. So where is the A? A is what? A is the surface area, right? So the surface area on the side. So what is that area? So if you this is your technology node, F, and you have height H. So your area is what? Pi F, which is the perimeter, times what? H, right? Divided by thickness of that oxide, which does not change too much. So you look at this with the scaling. That means you scale F. Of course, the C will decrease. So now you don't want C to decrease. Then what can you do from that equation?
You make the dielectric thinner.
Dielectric thinner, yes.
So it's going to leak more.
Yes. So that means you cannot really do this too much.
Change the dielectric constant.
Change your dielectric constant, yes, and make it even taller. So here we define that there is the aspect ratio, which is defined as the height over the diameter, and this aspect ratio will become higher. So let's look at each of those techniques in the following slides. So this is exactly what industry is doing to maintain this C, because naturally F is becoming smaller. So let's look at this by higher K value. So there is a concept called the EOT, equivalent oxide thickness. So this is equivalent to silicon dioxide. So we are changing the insulator material to higher K value, but we want to normalize the thickness to be the silicon dioxide thickness. So this is the conversion. So you have the silicon dioxide epsilon, which is about 4, and then divided by, let's say, your material, let's say hafnium oxide, for example, and then times the hafnium oxide thickness. So this is, let's say, another material. This is another material. And then if you convert that to be silicon dioxide, assuming the same cap value, you can do this conversion very easily. Because if you assume the same capacitance, then if you have higher K value, that means you can have larger thickness, right? Because here you can have larger thickness, larger epsilon, but then those two cancel each other, so you still have the same capacitance as the silicon dioxide. So in other words, the equivalent oxide thickness can be scaled down. It's like you are using higher K value. It's the same as you are shrinking the D value if you keep using silicon dioxide. So if you are using other material for higher K value, it's the same effect as you are using silicon dioxide but with smaller thickness. So that smaller thickness is called the EOT, equivalent oxide thickness. And eventually you want to scale this EOT because this A, as we discussed, is scaling, right? So then you want to make the D, this equivalent oxide thickness, also scale. So here this shows this EOT scaling over years by changing different materials and also different structures. We will talk about that later. But today, the EOT is below 1 nanometer. Equivalently, okay. This is like a 10 angstrom. This is like 1 nanometer thick. So, but of course, physically it's not 1 nanometer less because you are using high K material. The thickness may be a few nanometer. So, any questions here?